Now, before we begin, do you have any questions about time-independent perturbation theory? Now, one thing you have to pay attention to in the time-independent perturbation theory is the degeneracies. Now, we said that, okay, we first see what we had done. We have to do for the degenerate perturbation theory, but even if your spectrum is not degenerate, you still have a problem. Because the problem is, if you write, for example, consider the first correction to your wave function, psi 0, plus the sum over states different from this nth state of k and the matrix element of n h prime k. These are all the unperturbed states divided by en0 minus ek0. Well, I might have a sign mistake over there. Okay, so even if you have approximate degeneracies, that is, if you have states k whose energies are not exactly equal to en0, but very close. And in practice, that is most of the time the case, because the energies of a given system, it will always be scale like the inverse length, and the change in the energies will also decrease with the inverse length. So eventually, if you go to higher and higher excitations, your state will be very large, so the energy separation between these states will get very small, and so this number over here becomes very large. So if that number becomes very large, in that case, you cannot really talk about the convergence. So you have to talk about take the next correction, etc. Now, perturbation theory can work miracles. In certain cases, we can calculate certain quantities up to 24th the digit after the decimal point, and that's quite precise when it works, but there are many cases in which perturbation theory we just cannot use, mainly because this expansion doesn't converge. And so we need some alternative methods in such cases. Now, one of the methods that we will be using will be this variational principle. Now, variational principle is a powerful tool to study the ground state energy. Now, it might look quite restrictive. I mean, it only works for the ground state, for the first excited state. It works in some cases, not in other cases. But if you consider any physical system, eventually it tries to go to the ground state. Even in classical mechanics, the system always tries to minimize the energy. That's how the system behaves. So whatever you see around you is basically a system close to the ground state. So if you know the properties of the ground state, so you can understand a lot of things. Now, the variational principle is based on the observation that if you have any wave function, psi any wave function, any state, then this expectation value is always larger than or equal to the ground state. And it approaches the ground state more and more as the state psi becomes similar and similar to the ground state itself. Now, the proof is kind of easy. Since it's any state, you can always write it as a superposition of the eigenstates of your system. And then the matrix element of the Hamiltonian in this state would be just, you have a sum over n and m, psi m, am star, an, en, psi n, which is equal to n, m, am star, an, en. Now, the overlap of different energy eigenstates is 0 if they are different, and 1 if they are the same. Kronecker delta n, m. And so this is equal to sum of an squared en. Now, the ens are always less than or equal to the larger than or equal to the ground state energy. So this matrix element, which is equal to an squared en, Now, an squared, they are always positive numbers. So this is always larger than or equal to an squared energy of the ground state. Well, the energy of the ground state is just a constant, so which is equal to sum over an squared energy of the ground state, but this is 1. So this matrix element is always, whatever psi is, it is always larger than or equal to the energy of the ground state. Now, how to choose this psi? Well, it's arbitrary. You can choose whatever you want. And you can put some parameters, psi of r. It might depend on certain parameters. Let's call them A, B, C. In that case, this matrix element, it will be a function of these parameters. And you can just look at the minimum of this function with respect to these parameters. So f min, minimum value of f with respect to these parameters, will be always larger than or equal to the energy of the ground state. So this is a means of estimating the energy of the ground state. Now, one of the disadvantages of this method, though, is that in the perturbation theory, if the expansion is converging, we can improve the expansion, improve our approximation. So you just calculate more and more terms, and if all those terms are getting smaller and smaller, you can estimate also your error, how much far away you are from the exact value. You can give some estimates. But in this case, you can do better than the perturbation theory, but there is not really a means of estimating your error. You don't really know how much you are far off from the ground state. Now let's do is there any question here?
If these parameters are dependent to each other, then we minimize to that constraint.
Well, these are random parameters. I mean, why should you choose dependent parameters? Now, of course, one thing is, how do you choose the ground states? Well, the choice of the ground state is not really, how do you choose this psi? Now, we will see several examples that the physical intuition can guide you what kind of psi to choose. And if you have a potential problem, well, the shape of the more you get experience with quantum mechanics and the wave functions, you will see that the shapes of the solutions are not that different. The ground state always looks like a bump. That's always the ground state. And the first excited state has some node somewhere. It's 0 at some point. It's 2 bumps. The second excited is the first excited state. The first excited state will have 3 bumps, etc. This is the general shape of all the potential that you will come up with, all the wave functions that you will find. So let's do an example of this variational principle. One-dimensional harmonic oscillator. Can we find the ground state? So we know the Hamiltonian. This is equal to minus h bar squared over 2m. Now, since it's one-dimensional, it's just a derivative. Plus 1 over 2m omega squared x squared. So what kind of a trial wave function would you like to use? It should have some parameters in it which we can change to get the minimum of the expectation value of the Hamiltonian. So what would you like to have? It should go to 0 with x, either plus x or minus x. Some Gaussian. So psi you can take to be e to power minus a x squared times a. This goes to 0 as x goes to plus or minus infinity. So it satisfies kind of the boundary conditions. And we have to determine what a is first. And the a we can determine by the normalization condition. This is equal to a squared from minus infinity to infinity dx e to power minus 2ax squared. Now, in a sense, by the way, there is a constraint here on the parameters. We have these 2 parameters, large a and small a. Here we are solving the constraint. First we are solving the constraint and then minimizing with respect to the free parameters. Do you know how to calculate this integral?
Square root of pi over 2 times the square root of 1 over 2a, right? Sequence.
Do you know how to calculate it?
I can calculate this.
Using over, we multiply two of them for the integrals.
And then going to this circular coordinates. Yeah, okay. So this should be 1. So this already tells us that our wave function is 2a over pi raised to the power 1 to the 4 e to the power minus ax squared. So both the normalization and the exponential depends on a. Now let's calculate the matrix element of the Hamiltonian. Well, let's first look at the minus h bar squared over 2m times the Laplacian of psi, or del over del x. This is equal to minus h bar squared over 2m del over del x. Let's take the first derivative, 2a over pi raised to the power 1/4 minus 2ax e to the power minus ax squared. This is the first derivative. Let's take derivative once more. This will be minus h bar squared over 2m minus 2ax 2a over pi raised to the power 1/4. And that x is over here. So we have e to the power minus ax squared plus x minus 2ax e to the power minus ax squared. Can you see it? Right. So this is the second derivative. So let me simplify it slightly more. This will be 2 cancels 2, minuses cancel, h bar squared a over m, 2a over pi raised to the power 1/4 e to the power minus ax squared times 1 minus 2ax squared. So this is the kinetic energy. So minus h bar squared over 2m del squared by del x squared plus 1 over 2m omega squared acting on psi just gives me 2a over pi raised to the power 1 over 4. This is a. This is common in both terms. Both terms have e to the power minus ax squared. And from the kinetic term we have 1 minus 2ax squared times h bar squared a over m. And then we have plus 1 over, here I also have x squared. Plus 1 over 2m omega squared x squared. To a over pi raised to the power 1 over 4 e to the power minus ax squared. Let's just simplify this a bit. I can take the h bar squared of a over m also out. What I am left with is 1 plus x squared times m squared omega squared divided by a h bar squared minus 2a. Right? Yes. Now we can go for and calculate the matrix element of the Hamiltonian. This is equal to h bar squared a over m, 2a over pi raised to the power 1/2 times the integral of dx over x from minus infinity to infinity, e to power minus 2ax, and this parenthesis. So I just multiply this one with psi. So that's why I have the index exponent. I have e to power minus 2ax. And this factor just becomes, I have two of them, so it becomes the square root. H bar squared a over m 2a over pi raised to the power 1/2 ax squared. True. Let's see, 1 plus m squared omega squared divided by 2a h bar squared minus 2a times minus 1 over 2 del over del a times pi over 2a squared. Now, how did I get that? Let's see. If you take the derivative of the exponent with respect to a, then you get minus 2x squared. So instead of that x squared over there, I can write the derivative with respect to a and divide by minus 2 instead of x squared. Since it's a derivative with respect to a and not with respect to x, I can take that derivative out of the integral. If I take it out of the integral, what is left is from minus infinity to plus infinity e to power minus 2ax squared, whose integral is just pi over 2a square root. Okay, let's do it. We need to calculate this integral, right? E to power minus 2ax squared. This is the integral we want. That is one of the integrals that we want. This I can write as from minus infinity to infinity dx 1 over minus 2 del over del a of e to power minus 2ax squared. Because if I take the derivative with respect to a, I get minus 2x squared, and that minus 2 cancels the minus 2. I'm left with x squared times the exponent. Now the derivative I can take out, minus 1 over 2 del over del a from minus infinity to infinity dx e to power minus 2ax squared. And that integral I already know. Pi over 2a squared. Now this is one of the common tricks that you use to evaluate such integrals. If it was, let's say, x to the 4, then you would be taking the derivative twice. X to the 2n, you would be taking the derivative n times. X to the 2n plus 1, it gives 0 anyway. So now let's continue. So this is our result. This here. Now we need to take the derivative, simplify it. H bar squared a over m, 2a over pi square root, 1 plus m omega squared over 2a h bar squared minus 2a minus 1 over 2 m squared. Now when I take this derivative, okay, I will be bringing an additional factor of minus 1 over 2 and a factor of 1 over a. You see, this is a. This is, let's say, this is equal to minus 1 over 2 times minus 1 over 2a times pi over 2a raised to the power 1/2. That's basically what I'm using. Now I have the cancellations. This term will be the normalization terms will be cancelled. And I have h bar squared a over m 1 plus m squared omega squared over 2a h bar squared minus 2a times 1 over 4a
should minimize this.
Yes. Now this is the, well, let me just write it once more. This is h bar squared a over m plus h bar squared over 4m m squared omega squared over 2a h bar minus 2a. Well, let's see, this is h bar squared a over m. I have minus h bar squared over h bar squared a over 2m plus h bar squared m omega squared over 8a. Now this h bar also cancels. And I get a relatively simple final result, h bar squared a over 2m plus h bar m omega squared over 8a. Now if you plot it, I mean, it will have, as a goes to infinity, it goes to infinity because of the first term. As a goes to 0, it again goes to infinity because of the second term. So it just looks something like this. So there's a minimum somewhere over here. We have to find it. So let's find it. D by dA of h is equal to h bar squared over 2m minus h bar m omega squared over 8a squared. This should be equal to 0. H bar squared over 2m should be equal to h bar m omega over 8a squared. Well, h bars, they cancel. Here there's a 4. This is omega squared. So a squared is equal to m squared omega squared over 4h bar. And a is equal to m omega over 2, 1 over square root of h bar. Are you sure we didn't miss any h bars somewhere? So let's see. Here this is h bar squared, so this is h bar squared. So we don't have this h bar over here, there's no h bar over here. No h bar here, no h bar here, so this is h bar squared. This is h bar squared, so here we have h bar. So h min is equal to h bar squared over 2m. A is m omega over 2h bar plus m omega squared over 8, 2h bar over m omega. M's cancel, 1h bar cancels. Again, m's cancel, 1h bar cancels. So we have h bar omega over 4 plus h bar omega over 4, h bar omega over 2. In fact, this is the exact value.
KBT over 2.
Which?
KBT over 2. Energy over 2.
Yeah.
And in sound
Yeah, in thermodynamics, okay.
Is it, can you hear that?
No. Here we don't have the temperature.
It's energy. It's not electricity.
Well, the thing is, the initial wave function was already the exact wave function. with unknown parameters.
Which system will be considering?
Harmonic oscillator.
This solution we are doing? Is it one of the solutions? I mean, eigenstatement?
This one. If you choose the A to be equal to this number that we evaluated, it is the actual ground state. It just turned out to be so in this one.
Yeah, I didn't say the Gaussian as remembering it as a solution, but if it's...
I mean, that's one of the easiest choices, the first guesses that you would do. It's analytic everywhere, you can take the derivatives everywhere, etc. So it's a nice function. Let's give it another try.
Can you try maybe Dirac delta?
Dirac delta wave function. Well, let's try the Dirac delta wave function. Well, the problem with the Dirac delta that I don't really like is it's not normalizable. So that's what's not so nice about that. But let's give the exponential decaying function. A times e to power minus x if x is larger than 0. A times plus xa if x is less than 0. Why not? Or a times e to power minus a times the absolute value of x. We can try this one and see what we will have. Now, first we have to fix the normalization. Dx from minus infinity to infinity. This is a squared times twice the integral from 0 to infinity of e to power minus a x dx, which is 2a.
Minus 2a.
2a, you're right. So since the integral from minus infinity to 0 and 0 to infinity will be the same, I just take the integral from 0 to infinity and multiply by 2. Now this integral is just 1 over 2a. This should be 1. So this tells me that a, we can choose it to be square root of small a. So we know now we have our wave function, square root of a times e to power minus a absolute value of x. Let's take the derivatives of it. D psi by dx. What's the derivative? So let's say we have the square root of a. Well, we will have the a additional a e to power minus a absolute value of x, and if x is larger than 0, then the absolute value of x is just x. So when you take the derivative, there is a minus a in front, so there's minus 1. And when x is less than 0, then this is e to power ax without the minus sign. When you take the derivative, there is just a in front, so there is a plus 1. This is the first derivative. Now the second derivative, well, we can also write this in a different form. This is equal to square root of, or let's see, a to the power 3 halves e to power minus a absolute value of x times theta x. That's a step function. It is also minus theta x. It is 1 if x is greater than 0 and minus 1 if x is less than 0. Sine. Okay, this is the sine function. Let's write it. It's the sine function. Theta function is 0 or 1. This is the sine function. Now we need to take the second derivative. Well, this let's also write it as minus a psi signum of x, sine of x. Now the second derivative of psi is, minus a. Now the derivative of the sine function, signum function, is twice the Dirac delta of x. It changes by 2 as you go from the left of 0 to the right of 0. Do you agree that the derivative is the Dirac function? Good. Well, let's see. I want to find d by dx of signif of x. Okay, one thing is this is equal to 0 if x is not equal to 0. So if x is not 0, it's 0. That we definitely know. Another property that we know is d by dx of the signal function integrated over x. Let me write from 0 minus to 0 plus. Somewhere from the negative side of the 0 up to somewhere on the positive side of 0. And this is equal to signal function of x when x is equal to 0 minus to x is equal to 0 plus. When we are on the positive side of 0, then signal function is 1. Minus, when we are on the negative side of 0, the signal function is minus 1. So this is equal to 2. So this d by dx sine of x is such a weird function that it is 0 almost everywhere except in a single point, and its integral over that point is just 0, whatever the integration range is. So this is the definition of the Dirac delta function. So you are all familiar with the Dirac delta function. So these two properties are the definitions of the Dirac delta function. So that's why we know that the derivative of the signal function is the Dirac delta, twice the Dirac delta x, because it jumps by 2. Okay, so we have the minus a times the derivative of the signal function times psi of x plus signal of x times the derivative of psi. But the derivative of psi, we already know that it is minus a times the signal function times psi of x. So the second derivative of psi with respect to x squared is minus a psi of x times twice the Dirac delta of x minus a. Well, the signal function is either plus 1 or minus 1. Its square is almost always 1. Always 1, not almost. Well, there's a small ambiguity about what happens when x is equal to 0. But that's not relevant for us, so its square is almost always 1. So this is the second derivative. Now we can calculate h. This will be, now remember, a was square root of a dx from minus infinity to infinity, square root of a e to power minus a absolute value of x. This is our psi. So we have this psi star, we have another psi over here, so this is square. And then we have minus h bar squared over 2m times minus a times twice Dirac delta of x minus a. This is the kinetic energy. Plus 1 over 2 m omega squared x squared. Now let's say the Dirac delta is the easiest part to evaluate. Let's take out some of the factors. Let's start with the Dirac delta one. Minus 2a, the coefficient of Dirac delta. And then we have a from here. That minus h bar squared over 2m. And then what is left, the integral of Dirac delta is just substitute 0 everywhere, and that gives the wave function is just 1. The exponent just becomes 1. So this is the contribution from the Dirac delta part. Plus from minus infinity to infinity. Let's take the a out, dx e to power minus 2a absolute value of x times, well, minus h bar squared over 2m a squared plus 1. Well, let's also take that part. I mean, that part is just the normalization of my wave function. So that's also easy to evaluate. So this was the Dirac delta. Then we have plus minus h bar squared over 2m times a squared. That minus a times minus a is a squared. I can take it out. The remaining part is just a normalization integral, and that just gives me a 1. The only kind of complicated part will be the integral of this x squared. So let's write it plus 1 over 2m omega squared a. Now again, instead of integrating from minus infinity to plus infinity, I will just integrate from 0 to infinity and multiply by 2. Dx x squared e to power minus 2ax. This is equal to h bar squared a squared over m, the first term, plus the second term. The second term is h bar squared a squared over 2m with a minus sign. So those are the first two terms, plus m omega squared a times 1 over 4 d squared by dA squared from 0 to infinity dx e to power minus 2ax. Simply because if I take the derivative of the exponent, every time I will get a minus 2x in front. Minus 2x squared will just give me 4x squared. I don't want the 4, so I cancel the 4, and I obtain the integral of x squared. That integral is 1 over 2a. And I just need to take the second derivative. So this is equal to h bar squared a squared over 2m squared 2m plus m omega squared a over 4. If I take the first derivative, it will be a minus 1. If I take the second derivative, it will also bring me a minus 2 over 2a cubed. Now this minus cancels, these cancel, I have the a squared. So this is h bar squared a squared over 2m plus m omega squared over 4a squared. Now I need to minimize this one. Let me minimize with respect to a squared rather than a. The h bar dA squared, which is h bar squared over 2m minus m omega squared over 4a to the 4, this should be 0. So m omega squared over 4a squared is h bar squared over 2m. Now a to the 4 is h bar squared over 2m, which tells me that a to the 4 is m squared omega squared over 2h bar squared. A squared is equal to m omega over square root of 2 of h bar. Now we can calculate the minimum value of the matrix element. H bar squared a squared, no, a squared we already know. H bar squared over 2m times a squared is m omega over square root of 2 of h bar plus m omega squared over 4. Now 1 over a squared is square root of 2 h bar over m omega. Let's see, h bar cancels. here m cancels, omega cancels, m cancels. So we have h bar omega over 2 square root of 2 plus h bar omega over 2 square root of 2. H bar omega over square root of 2 or square root of 2 h bar omega over 2. It's just 50% larger. Again, the condition is satisfied. This is larger than or equal to energy of the ground state. Of course, this function is not that nice. It has this Dirac delta discontinuity. In general, we don't have such non-analytic functions. So the first choice will always be the Gaussian, in one dimension at least. In higher dimensions, you can have the e to exponentially decaying function with the radius, but in one dimension, you also don't have that choice. Now, there is a related theorem, or let's say a corollary. Now, we know that for any psi, then the matrix element of the Hamiltonian in this state is always larger than or equal to the ground state energy. So we get an upper bound for the ground state energy for any system. If this psi is orthogonal to the ground state, is 0. Somehow, if it turns out to be orthogonal, in that case, psi h psi is always larger than or equal to EF, which is the energy of the first excited state. Either you have to know the ground state function or you have to have an approximation to the ground state function. So the way you can proceed is start with a psi ground state for the trial function. Take a trial function for the ground state, minimize h, and you have an estimate for EG, let's say estimate, and psi g estimate. So you have an estimate for the ground state wave function. Now the next thing, find psi first excited state trial such that this trial wave function for the first excited state will be orthogonal to your estimate of the ground state.
For the energy estimate for the ground state, after we obtain it from the trial, how do we rearrange the new estimate for the ground state in the first line?
Now, in the first line, that is, your trial wave function will depend on these parameters that you have. You find the values of those parameters by minimizing the matrix element of H. For those values of the parameters, you have an estimate for the ground state. Yes, this estimate of the ground state, the parameters appearing in that estimate are obtained by minimizing H. So this way you can build up your trials for the excited states also. Now, of course, since you will be deviating from the exact ground state in general, your estimates for the first and the second excited states will get worse and worse.
We don't have any tool to correct it.
No, we don't. There's no systematics to calculate corrections to those. Just you can try to find a trial wave function that contains many parameters. So if you have many parameters, by choosing their values suitably, you can just fit any function in a sense. And by minimizing them, you can find quite a reliable ground state estimate. And then you can find a reliable first excited state estimate, etc. In the case of the harmonic oscillator, we started with this ground state trial, which turned out to be the exact ground state. Now, the simplest orthogonal wave function to that one for the harmonic oscillator, the ground state estimate, if you remember, it was e to the power minus ax squared, which turned out to be exact. For the first one, let's say b x e to the power minus ax squared. And this would be orthogonal to the ground state, and in fact, it will turn out to be the exact first excited state. But for the harmonic oscillator, we were lucky. So this is basically how we apply the variational principle to any system. Of course, the trial wave function, you can be guided by your physical intuition. And we will do some more physical examples like the helium ion or the molecular hydrogen in the next hour. Questions? So let's give a break now.